Yeah, hi. Thank you so much for inviting me to this amazing autumn school. I've already learned a lot about CP2K. My name is Anna, and I work with the Erlangen National High Performance Computing Center. So we're going to switch views now from the user perspective to the compute center perspective. And we're going to see how we can use GROMACS on GPU, how we can tweak a little bit of performance. This is what I thought we're going to talk about. So I'm with a bit of what is the GPU compared to a CPU. Then just a bit of how GROMACS started with GPUs, how we can install it, but yeah, and then benchmarks, results, and a bit of tips on how to set up some stuff, and what we do in the support. Okay, everything on this slide I took from this link that I showed here, so I'm not an expert on computer hardware. In general, you all know CPUs, so this is a general purpose processing unit. It has several serial instruction. I mean, you can read this all. It can basically do everything. We can calculate and compute everything on the CPU. Compared to the GPU, it has many cores, but less powerful cores. The clock speed, clock frequency is lower than on the CPU, and it uses simpler and specialized instructions. So not everything can efficiently be calculated on a GPU. In general, we use a CPU for the operating system. Everything we do on, not everything, nearly everything, we do on a laptop, on a normal computer, on a mobile phone. That's all CPUs. And a GPU we use for graphics rendering or machine learning. So if you're into computer games, you might have a graphics card in your computer at home. And we also use it for scientific simulations. So maybe you have a workstation in your office that has a GPU where you run. And we also have it in high performance computing. And we buy lots and lots of GPUs nowadays for all of the AI users and also MD simulation people. What you can also see on the pictures on the bottom of the slide is that they look similar. GPUs are actually not as big as you might have thought. The thing you see is the cooling and the fan, and the GPU is. So it's really small and really cute. Yeah, and it is flat, and it's not this big thing you put into your computer, or not even the big blades in a server. So the CPU is also just like this size. Okay, so how came GROMACS to GPUs? GROMACS is an MD simulation code, and it was first implemented for CPUs, and in version 4.5, that was in 2013, they started using CUDA to implement the offloading of non-bonded interactions, and then in 2016 added OpenCL support for the non-bonded interactions, but also increased the CUDA performance. Going forward 2 years, they now implemented the PME offload with CUDA. So electrostatic, the calculation of interstatic calculations could now, calculation of interstatic interactions, electrostatic interactions, okay, could now be computed on the GPU. And this continued with the offloading of bonded interactions onto NVIDIA GPUs and also the implementation of the particle mesh eval offload with OpenCL. So OpenCL you can use for NVIDIA GPUs, but you can also use this for AMD GPUs or Intel GPUs. Everything that doesn't use CUDA, basically. It is not as efficient nowadays, but it works. We also going to see that they switch to something else later. So 2020, they implemented the offloading on updates and constraints. So this is the calculation of updating of neighbor lists and the constraints that you put on hydrogen bonds in your protein or water or whatever you're gonna simulate. And they implemented the GPU direct communication for particle-particle interactions and particle mesh eval. GPU direct is also NVIDIA specific. So GROMACS and NVIDIA have, so the GROMACS developers and NVIDIA have a collaboration going on. So each of the improvements in GROMACS you can see is first released on NVIDIA GPUs, which I'm not saying is bad or good, I'm just gonna inform you. In version 2021, they tweaked a bit of the setups that you can now also, it was a bit weird. You could not use the updates and constraints before without the GPU direct communication. Now it's possible, and they also switched to SYCL for GPU support. So OpenCL is also, I think, a proprietary code base, and now they switched to SYCL because this is open source. If I got that right, I think it is. Further implementations and improvements then on the GPU direct communications and more support for Intel and AMD and also Apple GPUs. So the new Apple computers sometimes have a GPU on board of the CPU, and you can use OpenCL to build a GROMACS version to use on your Apple computer. Also, I recently heard that someone has compiled GROMACS for an Android phone. So it does run on Android as well. So yeah, I mean, this is really nice. It's not very fast, but it works. So ARM devices are nowadays also supported, which we can also see later on. What we finally have in version 2023 is that you can do a PME decomposition with CUDA and SYCL and also use a CUDA graph, which apparently is a nice implementation by CUDA and NVIDIA. I have never really been able to run that properly with any of the benchmarks I used. I'm just going to report this here. And the newest version is 2025, and they have now changed to AMD HIP for a CUDA backend for non-bonded interactions. So it's HIP, I don't know if you're familiar with that, but HIP is something similar to CUDA, but for AMD. And the syntax is basically everywhere where it says substituted with HIP, and that is called HIPify, and then you have, in theory, a code that runs efficiently on AMD GPUs. It is not as easy as it sounds, but in theory it works. So nowadays it is, with the different GPUs and the different vendors, it is basically needed that you have one code base for NVIDIA GPUs and one code base for AMD GPUs. them because the instructions don't work. It is a lot of code to maintain, but there's also, I mean, you could use SYCL for all of the GPUs, but it's not as efficient as using the vendor-based implementation of CUDA or HIP, basically. What is always ongoing with GROMACS is bug fixes and code improvements. They implement changes in SIMD, for example, on CPUs. So every year they release a new version of GROMACS with tweaks and improvements and nice new things. They also kick out things they don't need anymore or don't want to support because no one uses it. And we're also going to come to the importance of using which version you're going to use. We're going to see that this afternoon. So installing GROMACS on NVIDIA GPUs can be really simple. What we do in Erlangen at NHR at FAUs, we use SPAC, and it is a single line. As you can see on the slide, just SPAC install GROMACS, then use CUDA and don't use MPI. You can improve that a little bit if you want to install a special version, if you want to use a certain compiler, which CPU you're going to run, which CUDA you want to build, so which version of the compiler you want to use to install CUDA, which one to CMake. You can tweak everything. You can make it complicated or you can make it easy. I also linked the installation guide and the current release on the slides, but I don't expect that anyone who is going to work at a computing center will have to install their own version of GROMACS unless they have some special requirements that the compute center doesn't want to support, or it just says it's only you who's going to use it. Please try it yourself. Next, I'm gonna tell you which of the systems I use to benchmark all of the data that I'm gonna show you later. So these are the NVIDIA GPU systems we have at NHR at FAU. The upper two are the H100 systems. We have a big cluster with the H100. This is also what Robert said yesterday about the Auto system, that they have installed this and it's up and running. So these are the newest GPUs. Not really the newest. I mean, the really newest are the Blackwell, but Blackwell is not yet installed in the compute centers, really. Okay, so the Hopper versions. Then the previous version is the Ampere version. There we have the A100 and the A40 in Erlangen, and we ran all of our GROMACS and GROMACS simulations and setups and afternoon on the A100s GPUs. And then there's this Ada Lovelace architecture, which is quite lovely for MD simulations, really, because it has a high CUDA core count. It is higher than in the Hopper architecture, and CUDA cores are the only ones that GROMACS can use. So all of the nice tensor cores that are now on the NVIDIA GPUs are basically useless for GROMACS. And a really expensive GPU is looking at some CUDA cores and watching the CUDA cores do some things, but the tensor cores are completely empty. What I want to point out here, so the Ampere generation is the main workhorse in HR at FAU. They're very efficient, so we bought them especially for MD simulations in chemistry, biology, all of that. It works with CP2K, it works with Amber, they work with GROMACS. What else do we have? I think OpenMM, VASP. You can run VASP on GPU. All of that works perfectly on the A100 GPUs. what I want to show you here is that the power consumption on the systems can vastly differ between 1,000 watts for the GH200, so that is a Hopper architecture. The Hopper architecture is basically the same GPU as on the H100, and 72 watts, which is a server GPU. That is, it might not be perfect for GROMACS, but we're going to see later on that this is a really nice system in terms of energy efficiency. So I'm just going to go on. What I normally use as benchmarks are these 6 types of systems. We took the first 4. We asked some users if we could use their systems to benchmark them. So we have real-world benchmark systems, not artificially set up systems that don't use any outputs or have some settings that no one else uses anymore just because they run fast. So these are systems that have been used by users, that have been published, or whether it turns out, oh, it doesn't make sense in the end what I simulated. But it's fine for us. It doesn't have to make sense for us. It is a real-world system, and that is all that counts for us. The normal-sized systems that run on our computers are between, I would say, 50,000 to 200,000 atoms. That is the normal range. Some of the users, I see, I see maybe my systems, some systems are larger, so we also have users with 2.5 million atoms, but not on a regular basis. That depends on the group that works with the systems. Some people set up really big systems, some people set up small systems, but they can all work. That doesn't matter. Okay, coming to the benchmark results. Some of them they're not with the newest GROMACS version, but I don't think that it really makes a difference with the overall how do you say that? The overall things I want to tell you, the numbers would be a bit different with GROMACS version 2025. We're not going to only talk about the performance numbers in nanoseconds per day, so that is what GROMACS puts out at the bottom of the log files, but also we're going to compare the GPUs in terms of hardware, costs, and energy usage. So I ran all of the benchmarks on all of the systems, collected all of the performance data, and put this in this table. It's a lot of numbers. You don't have to really understand what is going on here. I standardized them to the A40 as a baseline. So this is what we can see here. They are all standardized. It's also in the top right corner of the top left corner of the table. So what we can see from these numbers is that the smaller systems give worse performance on the A100 GPUs than on the A40. So that's why the numbers are a bit lower than 1. But they give better performance. And the large systems give better performance on the A100. So this shows us that we need to pick the right GPU for the system we're going to simulate. Does that make sense? So we can have better performance on some GPUs and worse performance on other GPUs. It really is a matter of benchmarking. And yes, please?
Do we care about the memory bandwidth in the GPUs? Because if the load doesn't care about RTX cores, for example, and it just cares about core count or CUDA core count, do we care about how much RAM or VRAM does the card have?
No. No, we don't. Some of the code is compute bound, some of the code is memory bound, because I ran some profiling and it switches, and it doesn't really make a difference, no. We can never see that any of the simulations use the whole memory bandwidth, no. I don't know, maybe if you have 1 trillion atoms, but I don't know if that is feasible. Yeah. So looking a bit deeper into these numbers, we can see that on the Hopper systems, the small systems, it looks as if they give us a better performance than compared to the A40. And also the same is true with the big systems. They also show a better performance on the Hopper systems. But if we now look at the lower part of the table, we see that also the L40 and the L40S systems give us a better performance than the A40. So here the question is on performance, on hardware costs. I'm going to show you this in a minute because this is really interesting. So we can have, we can have nearly the same performance on these different GPU types, but the hardware costs are vastly different. So to see some trends with these numbers and between the hardwares, we converged the original performance data by multiplying these with the system numbers, the number of atoms. This gives this amazing table. Then we standardized it again to the A40, as we've done before. And to make it a bit easier for us on the eyes, I calculated the average. And from a pure performance point of view, the L40, this is the red line, doesn't look really like the other. And we also see that the Ampere generation, so the A100 and the A40, performance-wise, take a backseat compared to the Hopper generation and the Ada Lovelace generation. But that is only because they have less CUDA cores compared to the new generation. So there's no improvement in code. There are no differences in setup. The only difference here is the number of CUDA cores. So let's go over and look at the hardware costs. So because we buy the GPUs, we also need to look at some of the how much it costs and how many GPUs can we get for the money that we have available. Yes, the Hopper generation is expensive, and the Blackwell generation is even more expensive. But we can also, so this is the Hopper, and the L4 is, this is really nice. It only costs €2,500. I mean, this is something you could maybe buy for yourself and put it in a server somewhere. But compared to the H100, So if you want to buy a lot of GPUs, you go for the cheaper ones. If you say I need to buy the high-end GPU, then it's a bit of a number of how much money you have available, which can be really interesting in procurements and talking to AI people that tell you the previous generation of GPUs is not usable for us anymore. That wasn't a question, okay. That wasn't a question, okay. So we took the performance numbers, multiplied them with the number of atoms, divided by the and standardized it again and divided it by the hardware cost. And these are the numbers. Averaged it again. And it's really not surprising that the Hopper systems now have a bad look compared to the Ada Lovelace architecture performance numbers. So in terms of hardware costs and in terms of if you want to buy efficient GPUs for your MD simulations, it would be to go for the Ada Lovelace generation because of the price. And because of the performance, really. Because if you compare these two prices and then compare the performance to that, yes.
I mean, that's basically the price, considering the price to buy a GPU, but the thing is that you won't just buy the GPU, run your calculation, and then put it into the trash. But usually you will use it for several years. You will also have energy costs. So what about these?
So the energy costs are the same. So over 5 years, you have the same energy costs. So the costs for energy are the same as the procurement costs. So not really saving anything there. And then there's the question, I mean, when you look at the performance and there's no real difference, why should you buy the expensive Hopper GPU if you can also buy the cheap Ada Lovelace GPU? It then depends on, do you have other customers, other users that use that? Is it only MD simulations that run on these? Or do you also need it for machine learning or something like this? What we basically then decided to not allow the MD simulations users on the Hopper systems because it's too expensive and it's not worth the performance gain. Next up, we have the performance per energy. So we measured the power draw during the benchmarking. We're also gonna do this afternoon, not for the power draw, but for the GPU utilization. So you run the NVIDIA SMI as a loop, put it in the background, and then run your MD simulation, and then it puts out an amazing amount of numbers into a log file. You can analyze, so when we look at these numbers, this is the power draw for the benchmarks. And these numbers are significantly lower than what we saw on the data sheet from the GPUs. And that tells us that the GPUs are not used to their full capacity with these benchmarks. So not only are the tensor cores, the tensor cores are not used, they are in idle state, so the power draw is lower, which is nice for your energy bill at the end of the year. But in performance, we have not really have any gain. So again, I did the same procedure as with the other ones, multiplicated with the number of atoms, divided it by the power draw, standardized it to the A40. Yes, please.
Maybe stupid question, but have you also compared to the NVIDIA GeForce graphics cards? Because they're much cheaper than the Teslas. For example, that L4, which costs like 2,500, in reality it's equivalent of the 4070 or something like that.
Yeah, that's true, yes.
Is that the same, the same GPU performance? GROMACS could be the same?
They are compared to the L40. Yeah. I think the RTX 4050 or something. Yeah, I think they are at the same level as the L40, and they are much cheaper. The problem is we can't use them in a data center.
Users in the university, for example, if you have your own workstation, probably you can ask the IT to buy you.
Yes, yes. Yeah, that's what they do. Yeah, we have recently had someone ask us about buying the RTX consumer cards for a zip pool. Yeah. They're much cheaper. They run the same performance. It doesn't make a difference. We're just not allowed to install them in a data center.
Yeah, I guess the case of some AI implementation, some libraries, AI libraries not available to them, but for GROMACS it doesn't matter.
Yeah, for GROMACS it doesn't matter. Yeah, that's true. Yes?
I guess not really a question, but I read an article that in Europe, a university used RTX cards and NVIDIA found out and shut down their whole data center.
Yeah, that's what they do.
Data center, but on the workstation you can.
Yeah. But
if they find out that you use them in a data center, they're going to shut down your license.
So NVIDIA is basically forcing you to buy server-grade hardware that performs exactly the same as consumer-grade hardware.
Yes.
Great.
Yes. Yeah.
Brilliant.
I don't know what to say to that. So we did all the same, averaged this again, and in the end we see that the Ada Lovelace generation in this case gives the best performance per watts ratio, and especially the L4 is really nice in terms of performance per watts, although it didn't give the best impression when we only looked at the performance in the beginning. And the Hopper cards look bad. So,
I read the article actually about what's happening, and I also know from NVIDIA developers which are working for GROMACS. Yeah, of course I know them. So they saying like the Hopper cards was made specially for the AI, so their never was optimized for general computation, so they are accelerating only the inference of the neural networks. So that's why.
Yeah. And this is why, and this is, and then people come and see, oh, NVIDIA has published the newest generation, the Blackwell, and then they have all this amazing performance shown in their data sheet, and so many cores and so many flops. But in the end, if you use it with GROMACS, none of that is really worth anything because we can only use the CUDA cores. And then performance is, we recently benchmarked the RTX Pro 6000 server Blackwell. That is the consumer version of the B200. And it performs better than the B200 with GROMACS. And it's much cheaper. So the high-end, bestest, newest GPU version is not always the one we want to use with GROMACS.
I would say even we benchmarked here, it's not new benchmark, but even the old Volta V100 is also very fast with GROMACS. So and Voltas, old Voltas you can now buy on the second-hand market like for 500 euros or something like that.
In the beginning, when we had the A40, some of our researchers were a bit shocked about, oh, my results are already there. I don't even have the analysis set up. I don't know what to do now, because they were so fast. I think whatever card you have is worth using. Whatever card you have available, you don't necessarily have to buy new cards just because they are there. This is what we're going to tell our users. And the same numbers, I ran all these exact same analysis and benchmarks with Amber benchmarks, the standard Amber set, and the numbers are exactly the same. The colors are the same, the numbers are exactly the same. So MD simulations and newest NVIDIA GPUs don't really go hand in hand.
Have you benchmarked also, for example, Schrödinger software on this?
That would be nice.
No, because we don't have a license.
Because many of the people, for example, from farm companies, or even from universities, from drug discovery departments, they use Schrödinger software, so they're also interested in that.
But I don't know, but I think you can run Desmond for academic purposes without a license, and
you still need a license in the data center if you run it in the data center.
Even for data center usage.
They need to be agreement. Yeah. For example, in Finland have agreement with Schrödinger. That's CSC of Finland. They have agreement with Schrödinger that the academic users can use Schrödinger software on the data centers of CSC. But yeah, so it needs to be agreed separately with Schrödinger. Yeah.
Did we have a workstation at home?
Also with some of the software and licenses, they call home, so they're not, they could not be that easily used on compute centers because some of you need to set up a free port. Do you want to have your cluster nodes talk to a server in the US? I mean, that's all of the things we have to think about when using software. Yeah. I think I'm a bit too fast, really. Okay. Oh, I only see that. Okay, so now usage and how to use it on single GPUs, on multiple GPUs. What I'm not going to show you is how to use it on multi-nodes, so only on multi-GPUs on one node. Firstly, because I've not yet been able to run it successfully, set it up successfully. It needs a special GROMACS version with CUDA-aware MPI and... Yeah, and I've not been able to set it up. Also, the communication between the nodes will decrease performance again. So I'm not really sure if that is... I guess you're all interested in throughput or get your simulation done as fast as possible and not have 1 trillion atoms that would then be feasible to run on multi-nodes. So that is what I'm not going to show you here. And then for small systems, we can also use the NVIDIA MPS server. We're going to talk about that as well. So in general, GROMACS has a few command line flags that we can use to tweak performance. We have seen already on Monday that it can run. You can run it with just gmax mg run -s, put your trajectory in there, your TPR file in there, and just press play. It runs. It might not run with the best settings, the optimized settings, but it runs. But there's a few things we can use to make it run a bit faster and use the hardware optimally. So in general, for an explanation, the NT-MPI that we can see is the number of thread MPI threads. The thread MPI, so MPI stands for multiple message passing interface, not multiple, message passing interface. And it can be a single instance on your cluster that you can then invoke with MPI run. So there's a special MPI implementation. That is not what we're talking about here. GROMACS has implemented its own MPI version, and that is called thread MPI. And it is, in terms of vocabulary and use, the complete opposite of the MPI, the standalone MPI. So this is really confusing. I find it completely confusing, which then can lead to performance decrease if you don't use it properly. And that's why I'm going to show you how you can, I mean, you can try. I tried something yesterday with with the CP2K and GROMACS runs, and I decreased the performance, and I was really happy. So at least I found out what doesn't work. Okay, so the NT-MPI, the number of thread MPI threads, should be the same as the number of GPUs, which could also mean that you have a multiple of the GPUs. Because it is a rank. No, it is not a rank. Yes, it is a rank, but it's not a rank in terms of thread MPI. Okay, so, and the NTOMP is the number of OpenMP threads, so that is the, uses the OpenMP implementation, and that is the threads per MPI rank, and that should be set to the same number as the number of CPU cores you have allocated or have available on your workstation. For the benchmarks I showed you before, I set the NTOMP to 16 because for each GPU we have 16 host CPUs available, and we want to use each of these cores for our simulation. If you want to, you can use less cores, but then the cores are just looking at your simulation and do nothing. Also, if you tell GROMACS to use more of the OpenMP threads, so more of NT-OMP than are available as CPU cores, you're going to put more processes on one core, and that also decreases performance. So have a look at the settings, what you write in either what you have available on your workstation or what you allocate with your batch script. We can see this also this afternoon. And then set the NTOMP number accordingly. What we definitely want to do is pin the CPU threads to the physical cores on the CPU. What I observed when I started working with GROMACS and looked at the performance is that if I omit the pin option, the processes were jumping across the cores. They were sitting on top of each other. They were not pinned. Everything was a huge chaos on the CPU, and that decreased performance. And then I started with the pinning option. Everything is really ordered, each one thread per CPU, how it should be. They're not coming into interaction with each other. They're not slowing each other down. I think GROMACS can use something automatically that is not as efficient. As I said, it was jumping around. The next options are putting the GPU, invoking the offloading options. That is for the non-bonded interactions, the particle mesh EVA calculations, the bonded interactions, and the updates and constraints. GROMACS sets them automatically if it sees that a GPU is available, but it is not as efficient as if you tell GROMACS, you really have a GPU available and use it. Unfortunately, and that comes to the... Did you have a question?
Yeah,
go ahead.
If you have multiple GPUs on the same node, do you have to allocate each GPU manually? Or do you have to tell GROMACS to do it, or does it do it automatically?
That will be on the next slide. if that's fine, I'm gonna go. Yeah, I'm gonna tell you. No secrets kept here. Unfortunately, some of the settings do not work with all of the offloading options. So, for example, if you have the Nosey-Hoover thermostat, it does not work with update GPU. Also, if you're using virtual sites in your system, you can't use the update version for GPU. That is just because it's not implemented by the developers. I guess you could send them a Git issue. I'm not sure if they...
Some of these plans. So especially that virtual sites, because I guess it's already maybe in the main branch already. So not in release, but in the main branch on the Git. But what is not yet implemented, but in plans is you need, and you also need that for the virtual sites is these free energy perturbation simulations. They are not fully implemented on the GPUs, but they are in near future.
Okay, well that's nice. I'm looking forward to it because then I can tell people, it's fine, just offload everything to GROMACS. Yeah. What we're going to use this afternoon for benchmarking and to make all of our benchmarks a bit faster is the n-steps flag and the -v flag for verbose output. Don't use them in production. The verbose output prints the output to file every single step. You have an increased output, it can slow down your simulation. We do that for benchmarking purposes, so we can see something. But if I see a single user on our systems with the -v option, I'm going to send them a ticket and tell them to turn it off. Because it's not needed, it is network traffic, unnecessary network traffic. We don't want that, we don't need it. In the end, what it does, and it doesn't even produce important information. The only thing that it says is, oh, in this step, I have this and that force. And it tells you how long it takes to finish. That's all in the output with the -v. So turn it off for production runs. Now coming to the multiple GPU setup. Multiple GPU setups are complicated. It does not always run out of the box. If it does, you're really lucky. A lot of the times it doesn't. I have seen a severe decrease in performance if you set something wrong. It is not, I would not recommend trying something without looking or asking someone who has experience with that, because you can try a lot and it doesn't work. So the most important settings are the one at the bottom, the -NT-MPI and the NT-OMP. The -NT-MPI is set to a multiple of GPUs. So if you have 2 GPUs, you can either set it to 2 or 4 or 8. Also 6, but that probably doesn't work because it then has 3 in there, and GROMACS and some numbers is also a bit complicated. So a multiple of GPUs, because then you can run two ranks on one GPU if you set it to 4 when you have 2 GPUs. Does that make sense? Okay. And the NT-OMP should always be set to the number of cores, but as a product of NT-MPI and NT-OMP. Because it otherwise oversubscribes CPU again. And then performance decreases. And that's what I mean when I said the MPI names and vocabulary and GROMACS vocabulary doesn't really go hand in hand, because the name rank that GROMACS uses is not the same as you use in terms of GPU vocabulary. So GROMACS ranks and GPU ranks are not the same. What I've told you in the beginning was that GROMACS has implemented this GPU direct communication, and what that is a feature of the GPUs that they can communicate directly with each other without going through the CPU host. that makes communication faster, but you need to set some variables in GROMACS to use them. I think some of them are also set by default, but it doesn't matter if you set them manually. It just makes sure that they are there. So and GROMACS calls this halo transfer. So for this halo transfer, if you set these 4 environment variables, GROMACS will use the GPU direct communication and makes the simulation go faster on multi-GPUs. We're also going to try this in the hands-out this afternoon. And then there's this setting with the PCIe only servers and the servers that have NVLink available. So that also means look at what your compute center has available as hardware. For example, in NHR FAU, our A40 GPUs, they are PCIe only servers, and the A100 have NVLink between them. So NVLink means InfiniBand connection between the GPUs that is even faster than the PCIe only. So if we then use these settings, you can see on the slides, then you can also increase performance again. So everything that I show you, all of these settings, all of the flags, everything works favorable for performance if you set it correctly, especially with multi-GPU setups. It's really complicated. We're going to play around a bit this afternoon so you can see the differences. You can make your simulation a bit slower. You can make it a bit faster. You're going to see how it affects the simulation. And then, I'm really too fast. I have this NVIDIA MPS server. MPS stands for, I forgot it again. I have it on the other slides. It's something really amazing. Multi-something service. Do you have it? Multiprocessor service, yeah. Multiprocessor service, okay. Yeah, so what it does is it helps with the GPU usage. And if you run, for example, several instances of GROMACS on one GPU, invoke the MPS server, and then it's going to be faster. Because this the implementation of something, but it puts the ranks in order on the GPU, it puts the memory in order, everything is really nice and ordered, as before it was chaos, and then it runs faster. If you want to, you can try it this afternoon. I'm just going to show you this slide because we're going to try it. It's something we have used successfully for small systems or for replica exchange MD simulations with GROMACS. Also, if you run, I don't know, 100 instances of your simulation because you want to sample properly, you can run them all in parallel, use the MPS server, and it's going to go faster. That's it, really. Are there any questions so far? No? Okay. Then I'm going to tell you some stories from the support. Some users that contacted us and wanted some help with performance, that didn't know, tried something, and didn't really work out. And then they contacted us. And we benchmarked, we tried settings, and then came up with solutions with increased performance, send it back, and everyone was happy. We were happy that the resources were used properly. The users were happy because they had faster simulations. So the first example is a replica change MD simulation that ran with 26 replicas using GROMACS. The initial performance that the user gave us was 124 nanoseconds on 12 of the dual-socket Intel Ice Lake nodes, which they were, in the beginning, they were okay with it, and then they heard it could go. Maybe it could go a bit faster, maybe if we go to GPUs, maybe if we use more nodes. They didn't know. But yeah, we started this, and the estimated hardware costs in the beginning were a bit more than 60,000 euros, which is fine. I mean, it is what it is if you use expensive hardware and multiple instances of that. So we decided to run this simulation on GPUs. The problem is GROMACS, as I said, some numbers in GROMACS do not work very well with each other. So 26 is not a multiple of 8, so GROMACS will tell you I cannot run this replica exchange simulation. It just doesn't run. If you assign the particle-particle and electrostatic tasks to the GPUs per hand with this amazing flag that also had a bit of a few iterations until I figured out how to use it properly and which sequence of numbers would give good performance. Then it ran. GROMACS could then run the 26 replicas, and we were able to run it on 8 NVIDIA GPUs with a performance of 120 nanoseconds per day and an estimated hardware cost of a bit under 50,000 euros. So performance was the same as the beginning. We were able to reduce the hardware costs, and the user was happy. It ran. At the time, the resources, the GPU resources were free. The CPU resources were all blocked. So we put the user on GPU. They were happy. We were happy. But it took a bit of effort and a bit of trial and error to find the correct settings, and not to give up just if GROMACS tells you I can't do it. The next example is a big MD simulation with 2.5 million atoms. The user came to us. You want to use 8 NVIDIA GPUs. It only runs 11.8 nanoseconds. What can I do? I have tried so much, and with these settings, and it doesn't work, and I don't know what to do. And I need this because I need to write my paper, I need these results, So again, a bit of trial and error, benchmarks, playing with parameters, and all. So runtime parameters, not simulation setup parameters, only runtime parameters. So this is where I use these Halo Halo transfer variables for the improved communication, and then set the MPI and the NT-OMP to the correct settings. The user had tried something, but was oversubscribing the CPU. It wasn't the right number for the GPUs. It didn't work out. And in the end, we had a performance of 20 nanoseconds on 4 NVIDIA A40 GPUs, so we were able to double the performance on half of the hardware, which also made everyone happy because the user was happy, we were happy. It is great if we can work together and find a solution for the problems. And that didn't really work. Okay. I'm going to do it like this. So the last example I have for you is what do you do with modern code, what you can do with modern code on modern hardware. So in this case, it was a normal MD with 20 to 30,000 interaction sites, and they had run the simulations for a few years already with GROMACS 5.1.2. In that case, it was an 8-year-old version of GROMACS that is not supported by the developers anymore. It doesn't have any patches, but it ran on 5 of the Ivy Bridge nodes with a performance of 100 nanoseconds. In that case, we decided to check the setup and ran the benchmarks in a combination of, do we need the constraints on all bonds, or can we put them only on the hydrogen bonds? That was a question we asked the researchers. So this is nothing we were able to decide for them. If they say we need the constraints on all bonds because otherwise it doesn't work, then we accept it and try to tweak the performance from there. But in this case, we asked them, we said, okay, we're going to try it with constraints on all bonds, we're going to try it with constraints on the hydrogen bonds and see what comes from that. And then they also ran the Nose-Hoover thermostat, and this is not, the Nose-Hoover, it works, but the modern version of the thermostat would be the V-Rescale. And we also asked them, could we check the results? We ran the benchmarks for you. Are your systems still stable? Do you see the results that you're expecting? Is everything as you would like it to be? And we ran the benchmarks on modern hardware, so a modern code version, modern settings, and modern hardware. And we had, you see the numbers here. The numbers are different. So as I said, the Nose-Hoover, it doesn't work with the update, offload on GPUs. So it's a bit, the performance is lower with the Nose-Hoover settings than the V-Rescale settings. But in the end, an overall performance gain of 600% compared to the settings they had before. So it is worth thinking about your setups. It is worth changing to a new code version, changing to updated hardware. It doesn't have to be the newest and bestest and so on, but something that is not 10 years old, maybe, that has a bit more cores available, that uses modern SIMD implementations, and then we can increase performance. In the end, any questions there with setup? Okay, so in the end, what I can tell you on how to tweak GROMACS performance is to run benchmarks, ask for help, get in touch with your support at the local, either your IT support that has provided you with the workstations or the HPC support at your compute center. They know the hardware, so if you want to, you can ask, do the GPUs have NVLink? So you can use the optimized settings. Maybe you need, because you don't know how to find out how many CPU cores are available, try and find, you can also try it out and find it probably in the documentation. You can use LSCPU, for example, to find out information on the CPU using the command line. A bit of hardware knowledge is necessary to run simulations efficiently. They run out of the box. It does work. We have seen this. It does work. With a bit of hardware knowledge, you can tweak your performance, increase your performance, use the resources efficiently, and not have idle cores or idle GPUs that watch your simulation. I think that's it. I'm too fast. I'm so sorry. Do you have any questions? Yes.
I have a naive question. So, did you compile GROMACS with single precision or double precision? Or some users complain about single precision versus double precision? Yeah, what's your experience?
In general, we use single precision for all of the GROMACS codes. It normally is enough, maybe not for energy minimizations, so then double precision can be useful. There can also be some energy calculations where it could be necessary to compile with double precision. And yeah, I guess that would need to, we would need to recompile, but in general, we don't have it available. Yeah.
In general, I would say that if you do just a standard molecular dynamics, the single precision is enough, especially considering that GPUs have a very limited performance in double precision. So like they usually, like, especially in GPU versions, it's really suggests to use single precision. If you, even that fine when you do that GROMACS CP2K in single precision, it's still fine. It just means that you, when you do, as you said, like geometry optimizations might end earlier, for example, because it reaches the single precision limit, basically. So, in general, I would say that if you using the normal GROMACS with classical MD, just use single precision or default settings, basically. But for GROMACS CP2K interface, I suggest to use double precision just in case if you want to do geometry optimizations or something like that. Yeah. So. Yeah, but default for GPUs, default is always single. Should be always single precision because GPUs are working with double precision much slower than with single. Yeah.
The same is true for Amber. So our users, I think they have it compiled on their own server, but they use the double precision version for energy minimization, and then use the. I think it only runs in hybrid mode. With Amber, but then for normal production, for MD simulations, single precision is fine, or mixed precision,
Also, with single precision, you could also potentially, you can have a problem if you use constraints or bonds, because constraints could be sometimes, very specific systems, very unstable with respect to the precision. Yeah, for example, you have linear molecules, big linear molecules which have, and you're asking them to constrain bonds and angles or something like that, there could be stability issues with in single precision.
Then how much of performance are you giving up if you're using double precision then?
On CPUs, it's usually not really big change. It's like maybe 30% loss, but on GPUs it will be a huge loss, like factor of 4 to 6, depending on your GPU you use. Yeah.
Yeah, that would also, if you want to use double precision with GPUs, you also then need to look at your GPU model. Mm-hmm. So the A40, for example, doesn't have any double precision, so they can implement it in software, but that is slow. So the A100 would be the one to go there if you want to use double precision.
In A100, your double precision performance will be lowered by half, basically. Yeah? So you can do twice as much operations with single precision as with double on A100. But some NVIDIA GPUs, they just cut like almost completely the double precision, like A40. Yeah.
Yeah, they can do it in software, but it's really slow.
Yeah.
Sorry, maybe you explained it and I missed it. I didn't fully understand why the code did not run better on the bigger GPUs compared to the H100 compared to the L4.
So in terms of performance, it does, especially with the. Let me go back there. Where is it? Here. This one. So in terms of pure performance, the benchmarks would run on the H100 would be faster than on the L4. Especially on the L4, because the L4 only has 7,500 CUDA cores compared to the Hopper. Yeah. So,
why is it more efficient to run it on the L4?
L4 because it doesn't. It only uses 72 watts as a maximum.
Power consumption. Yeah.
The power consumption overall. Yeah.
The GPU is just more efficient, and that that means that GROMACS one is more efficient. Okay.
Yeah. In terms of energy consumption. Yeah. In terms of hardware costs, I think this will be this slide. It will be the L40 as well, because that one also has more CUDA cores, so your performance would also be. Better compared to the L4. Yeah.
And you had no, like as you showed, there was no use case in which you actually need the bigger GPUs. Then. Yeah. Could there be a use case?
I don't know. I haven't seen any so far.
Bigger GPUs usually can be used if you have a really huge system, like millions of atoms, and you need a lot of resident GPU memory. But yeah.
But that would mean a lot of memory, and the systems are normally not that big. So even the systems, I tried some artificial benchmarks from colleagues from LSZ, and they don't saturate the memory from the GPU.
Usually, yes.
Yeah.
Okay. Yeah. It's too small.
Thanks.
Yeah. Also here you did not put the actual, there is second important thing which you need to consider when running GROMACS, because you have first, what GROMACS is important for GROMACS is number of CUDA cores. Yeah. And the second one is clock frequency of that CUDA cores, maximum clock frequency, which are not here. I guess they also differ a lot between the GPUs.
So you overclock the...
Yeah. So, but do you have? I mean, the Hopper frequency.
This is something we have just actually we have just handed in the paper, I think yesterday, about core and memory frequency on GPUs. Yeah.
So this is also important.
But everything depends also on the power capping.
Yeah, actually, this for the data centers perspective, I don't know how it's working in the data centers, but how you are managing that power consumption of the GPU. So how fast your GPU switches from P0 to like P1 mode or something like that. So
I'm not sure I understand.
How fast the power state of the GPU switches in your data center?
You can pin the power state of the GPU to P3 or P4, can't you?
No, I think you need to have like sudo rights or root access to change it.
Yeah, of course.
But I mean, because the problem is, in some cases, the GPUs can warm up really long time, like several seconds they need to warm up to the full power, and because of this you can start losing some performance, especially if you run a bunch of small simulations.
Yes.
So it first tries to warm up, then the simulation ends, it cools down, and then again warm up, and then you have this.
Oh yeah, what I see, I think they're faster than the CPUs. So for the power measurements, energy measurements, I skipped the ramp up of the GPUs. I deleted because and that means it is important you run your benchmark sufficiently long enough. So that you get over this warm up. Yeah, that's true.
Because that warm up time actually it really depends on the settings you set in the drivers, in the configuration of the drivers on Linux as well.
Yeah.
That you can change, but it usually means that suddenly your data center could start to consuming a lot more power, and then you have a problem with power, with the incoming power. So that I'm usually trying to smooth it out, so it will not immediately jump to the full frequency and full power consumption, but it goes at over, I don't know, maybe several seconds or something like that, so it will slowly increase the power.
I don't think it makes a difference for performance, for production runs, really.
If it's long runs, yes. But if you want to run a series, let's say, of 10,000 runs for like 1 nanosecond each or something like that.
Oh, yeah. But that would be a case where I would recommend the MPS server, and then where you can run them in parallel. Yeah. So you don't have like warm up and cool down, all of that. Yeah. Also, with the overall with the power consumption, the problem with the newer GPUs is that they just draw so much power that you can't You can't operate them without a power capping anymore because there's not enough power available. Yeah.
So if suddenly, for example, you run 100 simulations and each using that H100, which consumes 1 kilowatt each. So suddenly your system will start to consume like 100 kilowatts immediately. Yeah, it can cause a problem in your network.
Also for, I do have this, there was this slide. With the MD simulations, they don't use the full potential of the GPUs. Even with AI, benchmarks we ran, some of them don't use the full capacity. So they run then at 600 watts or 750 or something, but not at 1,000.
How is determined actually? Do you know why it's how the drivers determine this? So they are basically checking what is the current usage of GPU and drive the power, or how it's managed from the NVIDIA side or from driver side, basically.
What do you mean with measuring?
No, why they cannot? So
sometimes because the settings, just the settings of the benchmarks or the AI workflow code thingy. Yeah, it's just the settings. We have some that can draw a lot of power, some that don't draw a lot of power. Yeah. It depends.
Yeah, because for example, GROMACS, why the GROMACS cannot use the full potential of GPU? Because it almost does not use the RT cores or whatever, so the tensor cores. Because GROMACS have a very little amount of operations of matrix multiplication in reality. So, but they're using a lot of CUDA cores. So it means that RT cores just waiting and they're not consuming power almost all the time, but CUDA cores consume. That's why usually if you run the simulation even on the RTX GPU, you see like its occupancy is usually like 80% or something like 85%.
It's like 91 or 92%.
Yeah. But this is because GROMACS does not use all full power of the GPU. It doesn't use some parts.
It depends on, and you can make it worse if you have not the optimized settings for your runs. You can like idle at 20%. GPU utilization, so you can tweak that also with the number with the NTMPI and NTOP settings. You can see this afternoon in a hands-on. I have some. We're going to look at the utilization and then play around with these numbers. All right.
Okay, thanks a lot.
All right. So we're going to have, I'm going to try and put this one away. We're going to have a bit of a hands-on session for GROMACS on GPU. I'm going to have, I have a few slides first that are now, so with a few examples of what I benchmarked and what I found out. So this example is a standard MD simulation where we have offloaded all possible calculations to the GPU. In this case, it was an RTX 2080 Ti. And you can see for the different GROMACS versions, the performance is very different. So in this case, the GROMACS 2022, it's not that impressive, but it was the early version of GROMACS, of that release. And the first release in that case wasn't the tuned one. There were probably a few bugs in there still. So the increase in performance here is not as incredible, but it changed with the further patches. So I think what I can show you here is that the newer GROMACS versions, they by themselves increase performance already. So without tuning any parameters on the command line, it's just the version of GROMACS. Then we're gonna do some multi-GPU setup, and it was the same simulation, but on a different number of GPUs. And you can see here, maybe you can't, but the middle column is 2 GPUs. And for the case, for all of the cases, is that the performance decreases if you use 2 GPUs compared to 1 GPU. And this is with the correct settings and with all of the optimized parameters. And the problem here is that the update flag only works on multiple GPUs if you also have update groups available. So constraints, for example, on all bonds don't allow you to put the update calculations on GPU. You have to run them on CPU, and that automatically slows down the performance. It increases a bit the performance for 4 GPUs, but it is still not the same as for a single GPU. Yeah, so that depends. You can try. If it works out, you're fine, and you can use it. If it doesn't work out, it's not really recommended. Then what we can also do, so these are the same numbers, and now we're going to calculate the performance gain, well, not in terms of percent and stuff, but just in numbers, and then calculate the parallel efficiency. Though the parallel efficiency is how we find out if the multiple GPUs that we use are actually beneficial for the overall performance gain. We're going to do this in the hands-on sessions, and I have some formulas for for you. So in the case of the A100 and this standard simulation, the gain in actual performance was 2 nanoseconds if we put it on 4 GPUs compared to 1 GPU. And the performance and the parallel efficiency is 0.25. So the parallel efficiency, if it is below 0.5, it means that more than half of the resources are idling. So parallel efficiency 5 is something that we as a compute center, when we see this is something we do not recommend it. You might be a bit faster, I mean, in this case, not really. But having half of the resources idling is not efficient for anyone, not for you as users, because you can only use half of the resources in the end, because if you allocate 2 GPUs instead of 1, you get billed for 2 GPUs instead of 1 GPU. So just to go down the table here, in this case for the A40, so the performance increases from 1 to 4 GPUs by 63 nanoseconds. So if you only just look at the numbers, it looks like there's an increase of performance, but the parallel efficiency is still below 0.5. So not recommended. The same goes for all of the other GPUs here and benchmarks and systems we tried. It might look as if the performance increases with more GPUs, but in the end it is a waste of resources. I just want to tell you that. So because we have had, I'm not saying that you're going to make this mistake, but some users at our center have made it, and they said we're going to allocate more GPUs because it makes our run faster, and then I showed them actually it makes it slower, and it is, doesn't make any sense. And then they were happy and said, thank you very much. and we were happy because no wasted resources anymore. The next system I want to show you is actually two systems. It is a membrane protein surrounded by explicit water and just a protein in explicit water. These two systems, number 3 and 4, are also systems that I have made available for you for the hands-on. And what I want to show you here is what we have already talked about, that the professional GPUs, in this case the V100, so this is a Volta generation, and the RTX, the consumer-grade GPU, it does not make a real difference in performance. And the same goes also for the Ampere generation, so the A40 and the A100, they basically show the same performance. So we don't need the professional and the double precision GPU for our MD simulations in terms of performance. What is also clear with these benchmarks is that if you double the size of the simulation system, regardless of it is a membrane protein or not, so we only count the number of atoms here, the performance decreases by 50%. So it's not really linear, because with more atoms comes more communication across threads, but in general you can roughly estimate what the performance of your simulation will look like. Then I have shown you that already, the benchmark systems. So these are the ones that I have provided for you for this hands-on, and the first 4 were from users, as I've already said, and the number 5 I've found in some repository for procurement on GitLab or GitHub, I don't know which one. And number 6 is a general STMV virus protein that is a standard benchmark in the GROMACS benchmarking suite. It's also available as a benchmark for NAMD and AMBER. So this is one of the standard benchmarks. They are set up in different ways, so different force fields, different pressure coupling, different temperature coupling, different thermostats, but it doesn't make any difference, really. I just want to show you what we can tweak regarding performance with some command line flags. Available, the GROMACS versions that are available are these two that we're going to use. It's GROMACS 2025, so the newest version that is available. Both modules have the thread MPI GROMACS version and the real MPI GROMACS version. They are invoked a bit differently, but I have examples for you. I have in a minute. And these other things I have already shown you. Because we're going to look at some setup options also, I just want to show you that these output control options are something to take a look at. Especially for system 1, this is going to be something where you can see the difference it makes if you write down output every 3 steps, or compared to system 2, where we write output, I think, every 1,000 steps, maybe 10,000 steps. Yeah, and as I already mentioned, the constraints, so if you are free to decide, use the constraints on hydrogen bonds only because it runs faster. And if you can use links instead of settle for the constraints algorithm, it will also run faster. I think the other things so for GPU code, it makes sense to use the CUDA version. So in most centers, the module names will have something with CUDA inside of them, or MPI or something. So if you want to use GPUs, use the CUDA version. For the thread MPI version, the MD engine is called GMX MD Run. That was different in the past versions, in like really old versions. And for the real MPI versions, it is GMX_MPI MD Run, and you also need either an S run, so the Slurm version, or the MPI run for MPI, invoking MPI. The other slides I've already shown you. I have just included them here for, to have them complete. And then we're going to go over to the Jupyter Hub and the hands-on document that I have prepared. So all of the benchmarks that are going to run, you can simply submit them via SBatch and then the name of the run, the file in your command line. Please ask if you have any questions. There are several people in this room who will be able to help you if you're stuck. In your Jupyter Hub, you should find in the exercises on day 3 a lot of this. So the systems, the TPRs, they are ready. There are also the scripts ready. And I have listed for you where you can edit some files, and I'm going to show you, for example, for the first script. So the first script, can you see that? It's large enough. You can also probably see. Okay. So we want to use a GPU. So we have the -- partition equals GPU. We want to allocate one node, and in that node, we want to allocate one task for the GPU, and we want to allocate 16 CPU cores. So that is the CPUs per task flag. And the last Slurm variable in this case is the GRES. So that tells us we want to allocate a GPU, an A100 GPU, and we want to allocate us one GPU. There's another script in your Jupyter Hub that will then have edited to 2 GPUs for the multi-GPU setup. So then we're gonna here load the GROMACS module, some flags that are recommended, so some variables here that are recommended by Paderborn, and then just run the GROMACS. The systems will run for 6 minutes. Some of the benchmarks will run faster. 6 minutes at most. And then we can just go through the benchmarks. I have made some suggestions what you can look at, compare, for example, System 1 and System 2. Change some GPU offloading for System 5. See what difference it makes if you set the variables. Or maybe we should go to the other. So here in the bench.sh, you can edit here the system you want, the number of OpenMP threads for GROMACS, the number of thread MPI, and then here all of the offloading options. There's a lot of documentation stuff here. Then we're going to load the modules. This is for outputting NVIDIA SMIs for outputting the utilization of the GPU. Then a long GMX MG run. This is just with all the parameters in there. And some printing of data in the files. In the end, you're gonna have a few files for all of the benchmark systems. I deleted everything that we don't need. That is automatically deleted, so trajectories are not important. Energy files, who needs them? So we only have the log files, and the log files will have, oh no, what I did, oh no. What did I do? Oh, okay. So the log files, it is a normal GROMACS log file. Nothing of that is of real importance right now. We can see that in the test run I did, the node was detected with 16 cores in a suitable GPU, compatible GPU. There was an AMD CPU, there's an NVIDIA GPU, just like we wanted to. Then GROMACS will tell us below, so this is the output of the setup of the simulation that you have set up before you run the benchmarks. That is already done here, and somewhere here it will tell us that the particle-particle calculations and the particle mesh eval calculations were run on GPU 0, so that is the GPU that we have allocated, and also that we have the bonded, short-ranged, update and constraints, and all of the PME tasks that run on GPU. And at the bottom of the file, this is the output we are looking for, is the performance number. So this run will lead to 126 nanoseconds per day if we run it for 24 hours in that case. So what I normally do is, instead of looking at the file, is just something like grep performance, and then it will put me the performance on the command line. Yeah. And then we have this other file that we're going to have is the power log file. And that is the long NVIDIA output file with all of the numbers, and that is not really interesting for us. Well, it is interesting, but not in this format. So I have printed it out to these files that start with GMX minus bench. And if we, that it didn't work. It should work. It didn't. Not everything worked the whole time. So there should be somewhere, maybe here. No such file. Okay, this is a bad example. So there's printed at the bottom of these GMX bench files, there should be the CPU usage. That also didn't work. Damn it. Okay, bad example. But at the bottom of these GMX minus bench, there is a number of percentage, and that is the GPU utilization. Yeah. You will get all of these files if you run the benchmarks, and then you can look at them. Have fun. I think you should all have the files in your Jupyter Hub, right? Okay. Yeah. Go ahead. Start.